Welcome everyone, and thank you for joining us in our third webinar of a three-part webinar series. The first webinar was targeted at executives and talked a lot about the business use cases in AI. The second webinar, which was yesterday, was really targeted at the IT personnel running clusters, and we talked a lot about InfiniBand and the importance of the network as a foundation of the cluster. Today's webinar is targeted at data scientists, and we'll be talking about the latest technologies from both NVIDIA and IBM that impact the data scientists. So you'll discover what NVIDIA RAPIDS is and why data scientists are using it. You're going to learn about the IBM tools that can be leveraged to automate data tagging and assist in the management in the full data workflow in order to improve your AI development cycle. So I'd really like to thank our two speakers today, Bob Crivello and Piyush Chaudhary, who is also known as PC, for their time today. So as most of you know, NVIDIA has pioneered accelerated computing, a supercharged form of computing. And today, accelerated computing is reshaping industries such as finance, government, healthcare, and manufacturing. And I like to refer to this form of accelerated computing as the beast, especially the new A100 GPUs. So IBM storage and data AI enables customers to seamlessly introduce AI initiatives in a hybrid cloud environment. So IBM Spectrum Storage delivers enterprise-ready storage that's secure, scalable, and fast, and is really all about feeding the beast, or the A100. So you likely imagine NVIDIA and IBM as hardware companies, but today don't be fooled. Today you're going to learn that these companies are winning in the AI space because of their investments in the enterprise-ready software that will accelerate the AI workflow. So our moderator today is Kim from R2i. If you have any questions, please type them in the Q&A. And at the end of the conference, raise your hand and you'll be unmuted. And I really, really encourage you to ask questions. This is where you'll get the value out of the presentation. So we'll get started. My name is Tamara Vandersloos. I'm Vice President of Innovation at R2i. I did 29 years at IBM as technical pre-sales. 7 years ago, I left IBM, and I'm one of the 3 founding members of R2i, which is based in Quebec with offices in Toronto and Ottawa. We're now over 40 people and growing. And I had the privilege to doing several service mandates around AI. I've helped build AI roadmaps. I've done running use case workshops to find out the best use case with the data that was already ready to go for a business to start. And I've had the opportunity to interview institutions actually around the world concerning their lessons learned and pain points around the operationalization of AI. So Bob Crivello is from NVIDIA, and he's director at NVIDIA. Bob is a solution architect is on the solution architect team and responsible for showing customers how to use NVIDIA products and to solve their business problems. Piyush Chaudhary, or known as PC, and also referred to as a rock star, has joined IBM in 1999. He's spent significant time working in the HPC organization on Spectrum Scale, which is IBM's high-performance clustered file system. So Piyush spent many years leading the Spectrum Scale development activities and focused on enabling analytics and AI workloads. Most recently has taken on the role as the lead architect for transforming Spectrum Scale for cloud-native and hybrid cloud deployments. So we'll get started. I'll do a quick review of who R2i is and talk about some of the common pain points that I've seen based on my interviews. Then NVIDIA will be talking about Rapids, and IBM will be talking about their tools around AI and the storage. And then we'll finish off with the next steps in Q&A. So who R2i is? Well, the big R stands for resources. We like to be known as resources, really an extension of your technical team. Most of our pre-sales people do both service engagements like myself and work as pre-sales. We do the 2 I's stand for I as infrastructure. We're predominantly an infrastructure partner. And so it's about we can sell the infrastructure or you can leverage our infrastructure. The I for integration is really impartition in French, which means cloud. So we have a large cloud environment. We have both synchronous, we have 2 data centers in Quebec that are in synchronous distances. We've recently opened the one in Toronto, and we'll be opening a 4th one in Toronto as well. So we like to be seen as your infrastructure partner for artificial intelligence solutions, whether it be the edge devices, the workstations, the servers, the storage, the networking. We can do the services from A to Z because I like to say that we walk the talk, meaning most everything we sell, we actually leverage ourselves, install ourselves. So we rack, stack, install, configure. We can do the operating systems and the tools required to run these workloads. We do services around AI use case workshops, building the AI roadmaps, or creating the AI lab. At a very high level, I did a lot of interviews and saw really commonality in the discussions on what the pain points were around AI. And I saw sort of 2 categories. One of discussions around the training times and how it's becoming a challenge because the number and the size of the data sets are increasing exponentially. We also see the AI models are growing in accuracy, and normally accuracy is going to come with the increasing in the size and trying to get that to fit into the GPU's memory. Keeping the GPUs at high utilizations rates has been another challenge that I've seen. So really, most people know this, that the data pipeline is actually 80% of the time on AI projects is actually spent on what I call wrangling the data. It's finding that data on those many siloed data sets. It's having quality data ready for ingestion, ensuring that's properly labeled, and the ability to move that data quickly for the training exercises or for the inference. So it's really about feeding that beast. So sorry. So I'll pass it on now to Bob, and he'll talk about Rapids and what's new in NVIDIA for the data scientist.
Thanks, Tamara. I'm going to go ahead and share my screen. And while I'm doing that, I would like to say on behalf of NVIDIA and myself, I would like to thank R2i and our partner IBM for the opportunity to present to you all. I hope you will find this useful. What I'd like to do is spend the first portion of my 20 minutes or so talking about Rapids, as Tamara mentioned, and hopefully you'll see that this is really something that can help to address that first pain point that she mentioned around training times. And the second part of my presentation, I'll be talking just briefly about GPUDirect Storage before I hand it over to IBM, and that will definitely be a technology that is really aligned towards the second pain point that Tamara just mentioned. So we'll talk about Rapids first, and Rapids is right here in this diagram, and the reason to look at this entire diagram is the idea that Rapids is actually part of our GPU accelerated software technology and software stacks. And there's a lot of stuff going on here. At the very bottom is where you would have your server hardware, and if you were having our latest GPUs in there, you'd have the A100 GPUs that Tamara mentioned. And on top of that, we have a variety of software layers. The GPUDirect Storage, which we'll talk about later, comes in this NVIDIA Magnum IO layer. CUDA is a technology that we have exposed for GPU accelerated code development for over 15 years. And then on top of that, we have a variety of different software technologies. You're probably familiar, or at least heard of the position that we have in the deep learning space, and we accelerate a variety of frameworks and workflows there. And we're going to focus for the next few minutes on Rapids. Rapids is really our technology for accelerating data analytics and accelerating machine learning in the traditional analytics and machine learning workbench or workflow. Of course, the only reason that I know of that people use GPUs for their processing workloads is to make things run faster, and so that's one of the most important things that we'll want to talk about. That training time pain point that Tamara mentioned is depicted on this slide. Actually, we're really focusing on two aspects of acceleration here. We're going to talk about acceleration in terms of data load and data preparation. That might be a little bit non-intuitive when you think about the GPU as a compute animal, but actually the GPU has high memory bandwidth as well. And so it turns out the ETL tasks that are associated with data load and data preparation in the data analytics workbench or workflow can take advantage of the GPU to do all of the data preparation that goes on there, and we can speed that up as well, and we'll see an example of that shortly. But machine learning training, of course, is an area that can take a very long time, and this is an example of some of the performance gains that we can get on a real-world problem. I believe this is around a 200 gigabyte data set that we're training on, and you can see that when we do the same workload on a cluster of CPU nodes, we can do that same workload on a very small GPU accelerated infrastructure using A100 GPUs and get dramatic speedups. So we observed that the RAPIDS open source data analytics and machine learning software has been adopted for a number of different use cases. Some of the use cases that we see most prominent are in the area of forecasting or prediction. We also see it being used for fraud detection, anomaly detection, and related ideas. And then finally, there's quite a bit of technology out there on the internet based on recommender systems. These are the methodologies that people use really to customize the internet and make it unique or specific to you. So if you're looking for a particular shopping experience and you want to have good recommendations, or maybe you're surfing your movie recommendation or your movie streaming service looking for recommendations, the recommender systems are what make your experience unique to you. And so this is a very important technology in the modern internet as well. So RAPIDS has some key libraries and some key aspects of the workflow that it accelerates. First of all, we've talked already about data preparation. Data preparation involves taking the data and getting it organized for use by subsequent activities in the workflow. Those subsequent activities might be basic analytic tasks like queries and visualization, but they could also be predictions or things that would depend on machine learning, for example, which we'll talk about in a moment. And as I mentioned, GPUs can actually accelerate the data preparation task as well. And if you're a data scientist, you might be familiar with the Pandas library, Python library that's often used for data preparation. And one of the key outputs or key things you create in Pandas is a data frame. And RAPIDS provides a library called co-df, which is essentially an analog of Pandas and is used to create a GPU data frame that subsequent operations will depend on for their data. And one of those subsequent operations that we talked about already is model training. If you're a data scientist, model training might involve you going into the scikit-learn library and choosing one of the ML algorithms there to get started with to make your prediction or whatever kind of machine learning you're doing. And we have an analog of scikit-learn called QML, and QML provides a variety of different machine learning methodologies that you can use to solve your problems. One in particular that I'll talk about is XGBoost. That's a fairly modern methodology that provides good performance as well as good applicability across a wide range of problems. And finally, we won't spend much time talking about it, but RAPIDS also provides a variety of libraries and methodologies to use for visualization of data. This can be really important in a machine learning workflow or any kind of data analytics workflow to be able to visualize the results of your data preparation, as well as perhaps visualize the results of whatever analytics or machine learning you're doing. So I mentioned that I'm actually going to be giving you all a demo here. We're going to take a look at a Jupyter notebook that has an end-to-end workflow. And in that demo, I will actually be demonstrating the use of XGBoost. So this is a decision tree technology, a gradient boosted decision tree. So if you're familiar with that, you'll have a pretty good idea already of how XGBoost works. XGBoost is a fairly recent of all the different technologies in a machine learning toolkit. This is a fairly recent development, and it provides good performance both on CPUs and GPUs. The GPU accelerated version is significantly faster than the CPU version, as we'll see in just a moment. One of the key things or value propositions we have around RAPIDS is that it should be fairly easy to adopt. And this is just a small piece of the Python code that you might use as part of your overall machine learning or analytics workflow. But the point I'm trying to make here is that we're using not just methodologies, but actually coding patterns that data scientists will probably be familiar with. I mentioned that there's sort of these parallel libraries like cuDF compared to Pandas and QML compared to scikit-learn. And that goes beyond just a statement at that level. It really means that from the standpoint of syntax, methodology, utilization, code design, that it's going to be very similar to the way that you're used to using your CPU tools for your analytics workflow. One of the, we have a variety of different customers who have adopted Rapids for accelerated analytics and accelerated machine learning. One of the ones we're really proud of course, is Walmart. They use Rapids because they have a very large machine learning problem. The idea here is that they have all kinds of SKUs, and not only that, but they have all kinds of stores in different locations. And so they have a very large prediction problem. They'd like to be able to accurately predict the number of a particular type of product that they need to have on the shelf in a particular store in a particular day of the year. And they have to do that across all products, all stores, and all days of the year. And they'd like to have the most accurate predictions possible so that they sell out, but they don't run short. That's the idea. And if they can maximize that, then of course they can maximize the efficiency of their processes. And so we're very proud of the fact that Walmart has adopted Rapids because of the scale of their analytics and machine learning that they're adopting. We're going to shift gears in just a moment to take a look at a very simple example of an end-to-end workflow using Rapids. Before I do that, I just want to reinforce the point that Rapids is an open source technology, so you can get it from GitHub and customize it or modify it if you'd like, but there's a variety of different ways to install Rapids. So all the traditional or common techniques like using Conda or pip to install it, these are all possible as well. Right before I shift over to my demo, I'd like to point out that you can very quickly get set up to use Rapids using our NGC cloud repository. So NGC is a repository of containers, of models, of scripts, Helm charts, and a variety of different resources that will make it very easy for you to get started, not only with Rapids, but really with a whole range of GPU accelerated technologies. So NGC is our cloud repository to do that, and it's a great way to get started very quickly to evaluate or to set up a development environment. So what I'd like to do now is shift over to my Jupyter Notebook. I've actually used an NGC ready machine in our infrastructure to set this up. It was literally just 4 commands. I had to do a Docker run command to load the Rapids container. I did a git clone command to actually pull this Rapids notebook, this Jupyter Notebook from GitHub. The third command that I did was to start the Jupyter Lab server, and then the fourth command that I did was actually just to paste this URL in my browser, which is now talking to that Jupyter Lab server, and that's how I'm running this particular Jupyter Notebook. So that whole process takes, once you're set up, that whole process takes like less than 5 minutes, thanks to NGC. So what I'm going to demonstrate with this notebook is an end-to-end workflow. What that means is we're going to start with data that is resident on disk, and we're going to look at various aspects of ETL, transform, and load of the data. And then we're going to go into model building and training using XGBoost. And in all of this, we're going to try and do it both on the CPU and the GPU, essentially the same problem in parallel on the CPU and the GPU so that we can compare acceleration. I want to point out that this is a toy problem so that things like training take a few seconds instead of minutes, hours, or days. But nevertheless, even with this very small toy problem, we can witness some significant speed ups between the CPU work and the GPU work that will hopefully motivate things. So because we're doing both CPU and GPU workflow, I'm going to load a bunch of stuff from scikit-learn, also XGBoost, also the libraries that we talked about like QML and QDF, which are part of Rapids. So that's our first cell. And what we're going to do is actually create a data set that consists of 3 different types of data blobs, if you will, that are created using standard techniques from scikit-learn. And we're going to create 3 different pieces of our data set, one called Swiss roll, one called moons, and one called blobs. You'll see what those look like in just a moment. So let's go ahead and build our data set of 5 million samples. And let's see, so we'll start to build these 3 different chunks. We'll stack those together. And we will generate labels for those 3 sets. So that the idea now is that we're going to, once we train our XGBoost model on this data set using these labels, which differentiate amongst the 3 different types of data, then we will make predictions, or we will then be set up to make predictions so that we can predict whether a particular arbitrary data point belongs to one of these, which of these 3 data sets, so to speak. So that's creating our labels, and we can see what our data set size is. And we will now split our data set between training and validation data. In order to visualize this data, we're going to use some plotting technology. And so the first thing is, what does the moon data set look like? So this is what the moon data set looks like. You can see they're kind of semicircles. Then we'll plot our blob data set, and that's our 5 different blobs. And then we'll take a look at what the Swiss roll data set looks like. It looks like this. And so you can think of these as 3 different data sets with labels corresponding to each of the 3. We can take a look at what they look like all together. Okay, so now these are now all merged, and you can see that they are definitely overlapping with each other in space. So this creates an interesting kind of classification or prediction problem. So as I mentioned, we're going to do a workflow both on the CPU and the GPU. So on the CPU side, we're going to use pandas, and we're going to create a data frame and then save that data frame to disk so that we can evaluate the load process. And once this is done, we're going to go on and actually do a similar operation on the GPU side. So we're going to use the library QDF in a few cells here. We're going to use the library called QDF to do the same type of work that we're doing, the same type of data preparation work that we're doing here with our pandas data frame.
Bob, I have a question. Is this going to work? Is Rapids working on a workstation and a single server and a cluster, all those 3, or?
Yes. Most of our GPU accelerated technologies work in a variety of different settings, even down to a laptop, for example. So there's definitely developers who develop on Rapids using their own laptop, and if you have an NVIDIA GPU in your laptop, you can do development that way. We also have a program called Data Science Workstation, which is sort of a professional workstation that's configured with GPUs in it and with all of the software stacks that you need ready to go. It's NGC ready, for example. And you can run Rapids in a workstation environment with workstation class GPUs and get acceleration that way. And then, of course, once you've actually done with all of the development work and you're ready to deploy it, most likely your deployment vehicle would be a GPU-enabled server as well. So pushing onward now, we're just doing some evaluation of data set sizes and things of that nature. You can see this is a pretty small data set. This is a toy problem, basically. We're now going to evaluate the load time for this pandas data set that we have, or this pandas data frame that we have already streamed or serialized to disk. And now our load time for pandas for pulling in this pre-processed data frame was 3.33 seconds. We're now going to look at trying to do the same thing using QDF, and we're going to try to evaluate the performance of the GPU load time compared to the CPU load time. So with QDF doing the same thing, pulling in the same data and getting it organized on the GPU, instead of 3.3 seconds, it took less than half a second. So our speed up there is going to be around a factor of 7 or 8. Again, this is just a toy problem, but nevertheless, even on this toy problem, we can start to see elements of the workflow that are running faster. The next phase isn't really mandatory for the demonstration, but what we're doing now is transforming the data. And one of the cool things about this is we're not actually using Rapids per se to transform the data when we do it on the GPU. In the CPU case we did, but when we transform the data on the GPU, we're actually using just general GPU accelerated computation here using a technology called Numba. And one of the things that this points out is in that first diagram that I showed you, all of our GPU acceleration technologies rest upon a common core. And that means that I can intermix different ways of solving problems. In this case, I'm intermixing general GPU acceleration. You could just sort of call this a CUDA-based processing approach that I'm doing here, and using that to accelerate this scaling or transform operation that I'm running. And in this case, we see that it runs much quicker on the GPU. And so if I evaluate the speed up comparing the CPU to GPU just for this transform step, we see that the GPU version is running quite a bit faster there as well. These next cells are just verifying equivalency between the data set, and so we would expect these last two cells to generate output here that looks the same, and we see that it does look the same between both our GPU and our CPU versions. So now we're on to the machine learning portion of this, and as I mentioned, we're going to use XGBoost, which is a gradient boosted decision tree. We're sort of pictorializing how a decision tree works here with multiple steps to get to the solution, multiple decision points to get to the solution. So we're going to prepare our data set for training. And don't worry about the pink output that we're going to get from this. This is just pointing out that we're using some deprecated stuff here. This is a little bit of an old notebook that I'm running here. And what we're going to do is set up our tree parameters for the kinds of decision trees that we're going to create. And now we're actually setting our parameters both for the GPU accelerated XGBoost and the CPU accelerated or the CPU driven XGBoost as well. And now we're going to do model training. We're going to train the model on the CPU first. And this will take probably, I think, around 40 seconds. So here we're actually running the fit process is the training process, and we're timing this. Again, the pink is just talking about deprecated stuff. We're going to wait for this to complete so that we can see what the time is to do the XGBoost model fitting on the CPU, and then we're going to do essentially the same step on the GPU as well. Okay, that trained in about 23 seconds of wall time. And when we run this on the GPU, we're going to see that it runs quite a bit faster, and we can then evaluate the speed up. And in this particular case, we got a speed up of about 16 for the model training. So we could go on and do model inference at this point using Rapids as well, comparing CPU and GPU, and we would observe that model inference runs quicker as well. But I think you get the idea now that Rapids allows us to do a workflow that's very similar to the kinds of workflows that data scientists are familiar with doing using CPU-based methodologies. And Rapids allows you to do a very similar workflow on the GPU and get significant speed up, even on this toy problem. So with that, I'm going to switch back to my slides now, and I'm going to talk just about one more idea before I turn it over to Piyush. So let's continue with our slides. And what I'd like to talk about now is GPUDirect Storage, which is part of our Magnum IO framework. As I mentioned, the problem that we were just going through there was a toy problem, so that the various activities didn't take very long and would fit in the kind of demo we wanted to do here. But for real world problems, data movement, data retrieval of data from storage is a very significant part of the overall workflow. It's the second of those two pain points that Tamara pointed out right at the beginning. And GPUDirect Storage is a methodology, a technology that allows us to accelerate that retrieval of data from storage as well. In a typical GPU accelerated workflow, even the one that we just ran through, there's very often some work that's done on the CPU prior to actually processing the data on the GPU. And therefore, we're typically going to transfer data from storage to the CPU and then from the CPU to the GPU. And this whole portion here becomes a bottleneck. It becomes a bottleneck because the CPU is not necessarily the fastest way to prep the data. We saw that in our previous demo. And it also becomes a bottleneck because there's latency associated with this path, and there is also throughput, bandwidth limitations that are associated with this path. And so the basic idea behind GPUDirect Storage is that we want to basically transfer data directly from our storage infrastructure directly onto the GPU, essentially bypassing the CPU. This means that we can actually use a faster path to do this. And in addition, the GPU for many types of calculation and preparation, as we've seen already, is actually faster than doing the same work on the CPU. So GPUDirect Storage, I'm not going to go through all the details on this slide, but GPUDirect Storage involves basically re-architecting, as you see on the right-hand side here, re-architecting the flow of data from storage so that instead of going from storage through our server infrastructure to the CPU memory being processed by the CPU and then back to the GPU, instead we follow this green line going from storage directly through our server logic infrastructure directly into GPU memory, and the work happens there. And this has benefits both for throughput and latency. And so with that, I'd like to stop here and turn it over to Piyush and let him pick up and talk about IBM storage.
Thank you, Bob. I'm going to start sharing my screen here. Hopefully. I hope everybody can see my screen. I'm going to go into presentation mode here. Okay.
Perfect.
Thank you, Tamara. What I have here are actually two presentations sort of smashed into one, and there's lots of dense content. I'm going to go through it fairly quickly, but I hope that it's still easily absorbable, and please ask questions. There's a Q&A chat session, and I'll be happy to return back and answer some questions. So as Bob did the handover, we're going to talk about first GPUDirect Storage. It's an awesome technology, and we've been collaborating with NVIDIA for the last almost a year on co-developing it and making sure that we have the absolute best implementation of it for our storage technologies. For what you're about to see has not been officially published yet. So I'm going to call it a preview. It's going to be coming out in the next approximately 2 weeks. And so outside of IBM and NVIDIA, you folks are the first one to see it. It's based off of an IBM ESS model 3200. This was announced in April and became available in May. And it's an awesome technology. It's so let's actually get into that really quickly. So the agenda is going to be, we're going to talk about that, and then I'm going to switch gears. I'm going to talk about data scientists' challenges that they face when they're working. They are working today on their laptops, they're working in their data centers, they're working in the cloud, and data management is a huge challenge. So how do we combine all of the performance stuff that you're about to see, and how do you tackle the data management challenges when you're working in this kind of a hybrid environment and still be able to do the job, right? The data scientist is supposed to be focusing on. She doesn't need to know where the data is and how it's connected and how do I move it. And we want to minimize the steps that you have to go through by going through various teams to make that happen. So I'm going to give you some idea of Spectrum Fusion, a new product that IBM announced also in April. It will be coming out later this year. We have it working. It's based off of 3 pieces of existing technologies that we're fusing together into a new enterprise container storage technology. And I'm going to be using that to demonstrate capabilities that we have in IBM Spectrum Scale and ESS. So let's get started. A quick little cartoon about what the configuration looks like. We have 2 NVIDIA DGX A100s. They're connected via their 8 compute links, and they're also connected via their 2 storage links. So each one of these DGXs has 2 HDR links that we're using for storage connectivity, and then the other 8 are for compute. Obviously, you can use the compute links for accessing the storage as well, but we are going to be focusing only on the storage performance, the performance of the storage NICs, because that's the recommended architecture that NVIDIA has. And when we do the official announcements of the results, we will also present, quote unquote, the hero numbers that you can get if you were to use all of the links that are available. But we're going to focus on storage links only today. The ESSs are awesome technology. It's a 2U form factor. It's got 24 NVMe drives. These are PCIe Gen 4, and roughly speaking, each one of these is able to deliver 80 gigabytes per second. So what you will see in here is not only that performance scales across the storage boxes, but it also scales across in the DGXs. So pretty cool stuff. You'll see a more formal, much more elaborate kind of announcement around these that go into a lot more detail, but I couldn't wait to show this. This is hot off the press. We just finished this testing over the weekend, and I couldn't wait to show everybody this. All right, so let's get into this. So what you're going to see on this chart is throughput. So here, these are been normalized to a single DGX A100, but you can imagine there's two of them running like this. And we have the throughput over here. We have three different colors that we're showing. One is how you would do things with just direct IO. And here's another optimization, direct IO plus CUDA memcopy to speed up the workload a little bit. Then is the GPUDirect, GDS, right? This is really what we want to focus on. And what you can see is that as we, and this shows you the config, right? That we're using 4 threads and 1 meg IO size. We can get slightly better numbers, actually, if we increase IO size, but we wanted to make it a little bit more reasonable, right? We're not trying to get the absolute peak numbers. These are actually what you can expect to see if you're running real workloads. And if you look at these green bars, they start topping out around at 84, 85 gigabytes per second. And that's no coincidence, because if you look at each of these NVIDIA DGX boxes, those 2 storage NICs that are available, right? That's what they will top out at. So what this is showing is that at this point, you can max out the available infrastructure bandwidth that's there. Also, the amazing difference between using, and by the way, the other numbers are through RDMA. So you're still using RDMA, but you're not using GPUDirect. So you're not skipping that hop and possible bottleneck that you have by going from the NIC to the CPU and then back to the GPU. Right here, you're going directly from the storage NIC that's bringing the data in directly to the GPU memory. So pretty impressive improvement in throughput, but it's not all about throughput. As we are seeing the NVIDIA GPUs being used for compute acceleration, not just for the AI workloads, but also in analytics. And especially when you start getting into analytics a lot, the latency becomes very important. And these are the latency improvements. So you can see that at the lower end, we were somewhere around a millisecond, and we get down to 200 microseconds, so 5x improvement, and it scales nicely. So here we were at like 1.6-ish milliseconds, and it's been cut down to roughly 800. So lots of improvements in latency as well. And so when you're doing lots of short IOs, when you're doing ETL workload that was being mentioned by Bob, when you're doing the data prep phase, right, you can see a tremendous improvement in throughput as well as the latency, which is very critical. I wanted to point out another metric here, which is the CPU utilization, the GPU utilization. So you can see that we are down in the 1 to 1.5% utilization, which is, we've been told, the best pretty much that anybody else seen with the implementation of GPUDirect Storage. So we'll see how that goes, but I just wanted to bring that number also, that it really does make a difference, right? We are making the CPU available for other workloads. You're running some other Spark analytics or something going on there. You're using it for other purposes. And the GPU, right? This frees up the compute resources to do what they're meant to do and not take over tons of cycles to move data around. So very excited about this result.
Those are really impressive results, PC. And for some of the training times, you're seeing probably overall improvements in training times, depending totally on the workload and how much data has to move, but up to 2 times, or?
Yeah, so that's a good point. It depends on the model, obviously, and the amount of data you're going to fetch. But if you take a look at this, right, the part where you're just spending time fetching data right? That's gone down in half, right? In terms of throughput. But also very impressive, I think, is the latency piece, because the latency is where it doesn't come across as much, but in those small accesses that are going on, and when you're doing ETL and you're doing data prep, right? This is 5x improvement, right? That's it just pays dividends. So it depends on the workload, what you're doing. You're going to see 2x, 5x, somewhere in there kind of an improvement.
Thank you.
All right, so let's shift gears now, and let's talk a little bit about Spectrum Fusion. Spectrum Fusion is our new enterprise container native storage solution, right? It's a new product IBM announced. It's going to be available, by the way, these are all forward-looking statements, so they come with caveats. But sometime in third quarter and fourth quarter, right, we'll see it comes in both a hardware sort of engineered solution like an appliance form factor, and it will also be available after that in a pure software-defined storage. It fuses together IBM Spectrum Scale. So Spectrum Scale is serving your data needs, and it has multi-protocol access that everybody knows. So we're going to be leveraging that, the object and the file access mechanisms, right? So we'll share data between file and object. You can access it either way, so you don't have to pick and choose for your applications or the frameworks that you have chosen for your workloads between one or the other. It has active file management, AFM. AFM has sort of been our secret sauce that's been hidden for too long, and now with the hybrid multi-cloud use case exploding on us, right, is really starting to shine. A lot of data, like when you're moving workloads around, you can move data, you can copy data. But the problem with copying of data is the challenges that you have around governance and provenance and the velocity and the gravity of the data, right? They could become super amplified. And so while it is a possibility, it is not a good way to approach that. What AFM does, it keeps a single copy of data, and it uses accelerated movement of data and caching mechanisms to make that single copy of data available wherever you need it. So we support in there movement between multiple Spectrum Scale instances, or between NFS and Spectrum Scale, or object and Spectrum Scale. So you can see we cover a big gamut, and you can copy and move data around, but use it only as a caching mechanism so that you can maintain that single source of truth, which is very important. And so what that helps you with is that data management challenge is sort of bounded. Your governance, your provenance issues are bounded. You don't have to now, how many copies of data proliferated across my enterprise? And just the basic laws of entropy will say that over time, these copies of data are going to diverge. And when they diverge, right, you no longer know what data at what time did you use to train your model, and can I go back and guarantee that? Because a lot of these models are being deployed in regulated industries like financial services or healthcare, and the provenance of that data model is very important. So it just reduces and removes all those challenges. So this virtualization and the single copy of data that you make available everywhere, that's very, very important. And the third piece, sorry.
At the end of the day, Piyush, for the data scientist, how does it impact them? It's like they don't have to worry about that anymore because that's already kind of built into the product fundamentally?
You're absolutely right. Just bear with me, and I'll get to exactly how it connects to the data scientist. And last two things I want to mention, it also includes Spectrum Discover, which is our automated tagging technology. So as you ingest data, it can take the system metadata and convert it into tags automatically, and also user-defined metadata, and use that to also tag data. So when you're looking for data, like how do I even know where the data is or what the data is that I should be using for my training and analytics? It simplifies that. It removes that burden. The last piece of this is it's got built-in data protection. So copying and snapshots and replication and backup, all of that is automated for you. So that's what Spectrum Fusion is. let's talk about the challenges of data management in this hybrid, crazy multi-cloud world. So enterprise customers, right, they have lots of different teams to manage their infrastructure and data. And the data scientist and the data engineer, right, like before a data scientist, like she can do her job, she's going to need to interact with the data engineer, and he's going to need to interact with all these different teams, right? There's a governance team, there's a compute resource management team, there's a storage management team that you have to work with in order to get your job done. And that's not really what, the data scientist, her focus should be on, right? She has an expertise that she should be focusing on that and not have to deal with all these issues. So what Spectrum Fusion does is gets away with all of that. And I'm going to show you some examples. So that's what the demo is going to be about. I'm going to show that, hey, by the way, I'm going to be using IBM Cloud Pak for data. This is our analytics and AI platform. And in there, I'm going to be using 2 services. There's a Watson Studio that you can use for your model development and just setting up your workload. And then Watson ML Accelerator that I'm going to use to sort of burst this workload to a second site where I actually have GPU-enabled resources to accelerate the actual training of the model and that workload. So without Spectrum Fusion, or without the capability that IBM Spectrum Scale, ESS, Discover, and Spectrum Protect Plus bring to the table in this new product, this is what you have to do, right? A data scientist requests data from the governance team, and I'm going to be using the A2D2 dataset, which is a automotive dataset that you're going to be it's used for training a autonomous driving model. So data scientists request the cluster team where to run the workload, and you're going to be told, oh, site 2 is there. So this site 1, where I'm using this Watson Studio and my Jupyter notebook, right? This could be my laptop, or this could be just a virtual instance that I'm getting in some local data center resource to do the initial development of my model. And then when I start doing the training work, right, I want to be able to burst that. So data scientists then request the storage team to replicate the data to that site. You run the actual workload on site 2, then you have to replicate the results back to site 1, right, where you want to actually make use of them. And then the storage team has to go behind the scenes and make sure that you delete the data set that was there so that they're not consuming resources and the data sets are just lying around. With Spectrum Fusion, we get rid of like 4 of these steps. Data scientists just say, hey, we're going to do my job, and I just run there. That's it. This is a big deal, right? This means that the data scientist, she can focus on what her area of expertise is. And so I'm going to go through these 5 steps by switching over to this. I apologize. I actually have a pre-recorded demo because I wasn't sure that, as you can imagine, some of these resources are highly in demand, that I would be able to get the access to the system. So I recorded this stuff. You're going to see 3 parts of the screen. Here is my Jupyter notebook, and I'll connect to a CPU environment to train the model. Then I'm going to use a GPU machine, enabled machine for this 8x speed up. And I'm going to show you that all of these steps all happening from a preferred environment, which is your Jupyter notebook, right? You don't want to be going through various tools to do this. You just want to be able to do it directly in the environment that you're familiar with. And here is a console window that I have that shows how data is being moved around without actually interacting with it. So I'm running out of time a little bit, so I'm going to just speed this up a little bit. First step, configuring the environment. Well, that's not a big deal, right? This is just, I'm going to skip through that, just user credentials, and I'm going to connect to the system via my Jupyter notebook, and let's skip that. Okay, train the model on the CPU. Again, not a big deal, right? This is locally where my Watson Studio is running, and I have data available here, and I'm just going to run it. And it's not a toy problem, but it's not a big one either, right? The data set is not that, for this piece, right, I've cut it down a little bit. So I have a 16 virtual CPUs, 32 gigs of memory, and it takes about 1,560 seconds to do this workload. Now it gets interesting. Now I'm going to say, I'm going to run it over here. And in order to run it over here, I need to find out what the right data is, transport it, use it, do the training, right, and then evict it. Of course, I can dive into, so there's the, hey, I have to go get the data. One of the ways I could do this is actually log into the GUI. There's a Spectrum Discover panel or a console. I could log into it. I can review all of my data sources that I'm connected to. Like, here's a bunch. And I can actually say, hey, this is the one that I need to do, the spectrum scale, and I'm going to use this A2D2 data set. But why should I have to worry about that, right? I can actually just, Spectrum Discover is a tagging system, so I just search for car, and it just finds all the data sets that of interest and goes and grabs all that data for me. And I think it takes like 7-8 seconds here to do that. And then it says, these are all the data sets that I found that met your tagging criteria. This, by the way, it scales brilliantly, right? The Spectrum Discover, it has the, as you're ingesting data, it can do hundreds of thousands of objects per second and automatically tag all the user-defined metadata, the system metadata that it finds, and it automatically tags all of the data. So when you're searching for it, right, it really simplifies a data scientist or engineer's job. Like, where the hell is this data, and how do I go get it? But what I want to show you here is I don't want to interact with that Spectrum Discover console. I don't want to leave my Jupyter notebook. I want to stay in here. So I actually do a REST API query to Discover and finds this. This is what I need to go find. I tell it that, execute this piece, and it goes finds everything for me. So I just showed you that Discover console for comparison purposes, but I don't ever have to leave my data set here. So I just go say, this is what I need. It found all the data. Then I say to Discover interacts brilliantly with AFM and say, now go cache it for me. So this is what this REST API is doing. And you can see here in the console in the bottom, here you go. 30,000 files, 30,000 files. It's caching all of those. And they're available now. So very quickly, right, it went through those 5 data sets. It found the right data for me. It brought it to my second site. And now I just start running this training model on the GPU system. And the same thing that I had run before. And let me accelerate this a little bit. And it runs, let me see. There you go. It's going to run that, and taking a little bit more, and it run it in 200 seconds. So you got an 8x speed up by running in this GPU system. And at the end of it, right, this is also fairly nice that I'm going to evict the data and say, I'm done with it. Right? And that's sort of the end of the demo here, right? And you can see that it's very jam-packed. I am actually staying all the time in my Jupyter notebook, and you see the data is all gone here, right? What's very cool here is that you can take your regular Jupyter notebook, you can use the Watson Studio console, you can work with Rapids in there. This system is very open. It has all the APIs right built in. It's very, very simple. It's all done for you, and you are no longer burdened with all the challenges of data management and, hey, how many copies do I have permission, and who's going to move the data for me? All done for you. It's all transparent. So I thought, taking some of the performance aspects and the data management aspects and just bringing it in a simple demo, right, might sort of hopefully resonate. So that's all I had, Tamara.
Thanks, PC. That's awesome. I could really see how this would be helpful, and I've seen that a lot as being one of the pain points, actually, in especially in the federal government space, not knowing where their data is, and then really worried about the governance. So you're saying these products, the Fusion will encapsulate all the products together, that it's going to enable that. So the data scientist doesn't have to worry about it anymore, and he'll only see the data he has access. And then anything that he uses, it'll be for governance reasons, it'll be aware of what it used, right?
Absolutely, right. And you can use it with Fusion. You can also use it directly with Spectrum Scale. I just use Fusion because it really brings it all together easily in a single place. And of course, it's already container native, which is where we think data scientists are operating these days, right?
And security is all being top of mind on the businesses as well, on making sure that what data they're using and and making sure it's being labeled. So I'll share my screen on. Just get my presentation up to finish up. Come on. And I'll just show it. You're seeing my screen now?
Yes.
Perfect. So we're about to finish up, and I just want to discuss what some of the next steps could be for our customers. We talked about this being the third part of a three-part webinar series. So there's 3 others that they can share the links for, and there's replays so they can listen to them. They can reach out to us, to R2i, for a personalized session, whether that be on use cases or in any of these tools that you've heard about today, because we kind of did a quick overview of a lot of subjects. But if any one specific subject interests you and you want to go deeper, we will set that up for you. We can do workshops and service engagement. So to reach us, you can either email me directly at tamarav@r2i.ca or info@r2i.ca, and we'd be happy to have further discussions on any of the topics if some of the pieces resonated with you. So this is the time, if you have any questions, that we open up the floor. If there's any questions. Did you see any, Kim, in the Q&A box?
There's a question we already answered about training. So if you want a link to get access to the NVIDIA courses, there's in the Q&A section. And we have another question. The question is there a beta version of Fusion that clients can test out before official release?
So I was about to answer that in the chat, and I will do that so that if you record this, right, you'll capture it. But no, the short answer is there is no beta version available right now. When the appliance version comes out, which is in third quarter, right before that, there will be hosted betas available so that you can remotely connect to the systems and try them out. And I think the software-defined version is really where you want to try it out for demo, POC purposes. And so that will hopefully it will be available in fourth quarter.
So the first piece that's coming out, the appliance, and there will be a version that people can connect to do POCs?
Yes, it's going to be limited because we don't have too many of these systems available before GA. So we'll have to go through our IBM technical specialist, request access, and see you can get that. But then hopefully in fourth quarter, we'll be doing a preview of the software-defined version, and that one you can just use and get your hands on, hopefully.
Perfect. And we are in time. We've still got a few minutes. Are there any other questions, Kim? That
no other question.
Perfect. And maybe I can just ask a question, which is one I often ask, and PC and can answer that. What do you see as the pain points for the data scientist specific? Mine were generalized, but what are you seeing as the big pain points for data scientists?
I think it's the bureaucracy and the challenges of the data management in the enterprise that I usually am struck by, right? That you need a big team of data engineers to work on getting the right data into the right location, curating it, making the the gold version of the data that has all the proper labeling, and then all the fields are just so that then you can actually use it, right? So yeah. That piece, at least to me, seems very, very onerous, because I think the tooling that's there, like you can Anaconda and Rapids and IBM's Cloud Pak for Data tooling. There's lots of good tools to actually do the training part, right? There's a lot of good acceleration libraries available. There's NGC container stuff that gets them going really, really quickly. But it's the all the stuff that has to happen behind the scenes, that is a challenge, right?
Yeah, it's that 80% of the time is spent on that data wrangling, finding the data,
exactly.
labeling the data, and then getting that data, having the pipeline. Because I've seen a lot of POCs, and what I saw was that data came across on a USB stick, right? And you can't take that to production. So I've seen a lot of like, yeah, we got a POC, we've got great values, we improved our predictions. Now what do I do? And it's that data pipeline of taking it into production that I've seen as a big issue. So I'll ask the same question to Bob. What do you see? Is because you have a different perspective. We have kind of the storage and the data perspective on the IBM side, and NVIDIA really sees the, the GPU's perspective. And what do you see, Bob, as being the big pain points?
Yeah, I would probably reiterate what you pointed out, Tamara, as the first pain point, and really expand on it. That being the time that it takes for tools to do their job. So NVIDIA has a picture that we like to talk about called a day in the life of the data scientist. And it points out a few things. First of all, it points out that the data scientist evolution or workflow is very often iterative, meaning it's not typical that you get everything just right the very first time. So you have to tweak things and run your tools again, and tweak some more and run your tools again, and tweak some more and run your tools again. And so if the tool execution time starts to become significant, like hours or days, it really stifles that investigative, iterative process of trying to optimize your solution, trying to come up with the best possible answer based on the data set and the features that you're able to identify. So when you can accelerate the tool processing time, then it really opens up additional areas for data scientists to work to optimize instead of spending their time waiting on tools to provide answers. So that's really, I think, one of the key pain points. And we believe that by providing accelerated solutions throughout the stack, that we're going to enable data scientists to not just get the work done, but actually to do a better job.
Okay, perfect. Thanks, Bob. And PC, you were about to say something else when I cut you off. Did you want to finish your sentence?
No, I was just trying to reiterate a small portion of that piece, right? That it's you develop you do your model development or something in a virtual environment, right? You small set of data in the cloud or something, and when you have to do it at large scale, right? And that's what NVIDIA has been focusing on now, and we are sort of connected at the hip there, which is it's easy to do this when you're doing a POC or just trying to play around with it. When you have to take it for a large automotive company, large telco company, financial services company, healthcare, life sciences, right, and governments, where they have gobs and gobs and gobs of data, and you need stacks of DGX A100s, right? The infrastructure is important, and then scaling all of this up is important. You don't have the luxury of trying to do this stuff across hundreds of GPUs and say, oops, it didn't quite work. Right now, let me reiterate what you're used to doing, right? So you got to get a lot of that initial data lifecycle under control and check, so that then you can make good use of these really, excellent and scarce resources.
Yeah, thank you. And it really is. It's probably more than 80% of the time spent on that data wrangling today. The data science is a kind of a simple, a relatively simple piece of the puzzle in terms of timing. So thank you. I think we've hit our time. Is that right, Kim? Or we went over by a few minutes?
I think we went over, but it's okay.
All right.
So thank you, everyone.
So I want to thank everyone for joining the webinar, and thank you very, very much to our two speakers today. We really appreciate the time you've spent with us.
Thank you for the opportunity.
Thanks, everyone.
Thanks.
Take care. Bye-bye.